0. That has been a good problem, and take some time and practice this problem. Just now look at the concept of force on a charge moving in a magnetic field. Well, electric current is caused by the motion of electric charges. So if a conductor carrying an electric current experiences a force, it means an electric charge moving in a magnetic field must experience a force. So a moving charge is equivalent to an electric current, and hence it has a magnetic field around it. As a moving charge enters a magnetic field, the two magnetic fields will interact, producing a force on the moving charge. Now, this force is proportional to the magnitude of the magnetic field B and the component of the velocity of the charged particle at right angles to B. Now, that means the force will be significant only if the direction of motion is at right angles to the direction of the field. If the charge moves in the direction of the field, there will be no force on it. There will be force on the charge only if there is an angle between the direction of the field and the direction of motion. And the force will be maximum when that angle is 90 degrees. So, a charge Q moving with a velocity V at an angle theta with the magnetic field B will experience a force given by, this is the equation, F equal to QV cross B, where QV is the first vector and B is the second vector. That again is a cross product, and we can write it like this: QVB sine theta. And that means this quantity is maximum when sine theta is 1, and sine theta becomes 1 when that theta is 90 degrees. So the force is always at right angles to the direction of motion, and it doesn't speed up the charge. This force will not make the charge accelerate in the direction in which it's moving. Why? Because if the motion is in that direction, the force will be at right angles to it. Now tell me, what does a force at right angles to a motion do? When an object is moving, a force at right angles to the motion will keep the object in a circular path. So, instead, the direction of motion is continuously changing, making the charge to move in a circle. So, if a charge is placed in the XY plane, let me see if I can have a diagram. Now here, I have the XY plane, and these dots indicate the magnetic field coming from out of the board. The magnetic field is actually coming out of the board, that is, coming towards you when you are watching. Now, a charge is placed in the XY plane. This is the XY plane. At right angles to a magnetic field in the Z direction, then the charge will move in a circle like this. Now, since the velocity v of the charge is always at an angle to the direction of B, the force will be QVB if that angle is a right angle. If theta is 90 degrees, that sine theta will be 0. So, in this case, the angle between the magnetic field, which is in that direction, and the direction of motion in the XY plane, the angle will be always 90 degrees. So the force will be QVB. Now, this is a measure of the centripetal force that makes the charge move in a circle. Therefore, we can take this quantity QVB and set it equal to the centripetal force. What is the equation for the centripetal force? mv squared over r, where m is the mass of that charge, v is its velocity, and r is its radius. So QVB equal to mv squared over r. And we can use this to solve for r, the radius of the circle, r equal to mv over qb. Now, what is the period of a circular motion? The period of a circular motion is the time taken for one complete circle. Now, that is, I think we can calculate the period, the time taken, as the length of the period, the length of the circle, that is 2 pi r, and divided by the velocity. Is that right? Yes. The period t is 2 pi r. 2 pi r is the length of that circle, and divided by the velocity, that will give you the time taken for one complete circle. Now, replace that r here by mv over qb. That gives me 2 pi times mv over qb over v. And rearrange it. That gives me the period t is 2 pi m divided by qb. In other words, the period t doesn't depend on the velocity. Alright, if period t is 2 pi m over qb, what is the frequency of such a motion? The frequency and the period are inverse of each other. So the frequency will be qb divided by 2 pi m. You may not be able to see that on the screen very well. Let's solve another problem. An electron traveling at 3.5 times 10 to the 7 meter per second enters a magnetic field of 0.056 Tesla at right angles to the direction of motion of the electron. Calculate the centripetal force on the electron, its period and frequency. Well, we have everything that we need. The radius of the circle described by the charge will be mv over qb. And using the standard values of m and q of electron, do you know the mass of an electron and the charge on it? Well, mass of the electron is 9.1 times 10 to the negative 31 kilogram. Its velocity is given. The charge of an electron is 1.602 times 10 to the negative 19 coulombs, and the field is 0.056 Tesla, and that gives you 0.0035 meter, and that is the radius of the circle. And we need to find the centripetal force. Centripetal force is mv squared over r. And we know all that quantities. M we know, V we know, R we calculated. And substituting that gives me 3.2 times 10 to the negative 13 Newton is the centripetal force. Well, what is its period? Period is 2 pi r divided by v. We know all those values. That is 6.3 times 10 to the negative 10 second. Well, if you know the period, you know the frequency. Frequency is 1.59 times 10 to the 9 hertz. That's a good problem, and you must be familiar with problems of this type. We will now look at another interesting concept, torque on a current carrying coil in a magnetic field. If a coil of wire is placed in a magnetic field, how will it behave? I can make a coil of wire by taking a wire and winding it on a frame like this. Now, I'm actually making a coil. Now, imagine there is a magnetic field here coming from the board towards you. Now, let's take Fleming's left-hand rule. The magnetic field is from the board towards you, that is the forefinger. And if the current now flows on this wire here in this direction, middle finger, then this end must move up. That means if a current flows in this coil, which is in this direction, that is towards me on the right side, there you got the magnetic field towards you, the current towards me, then this end must move up. Now, because of this coil, if the current is flowing towards me on this side, then the current must flow away from me on the other side. That means if this end experiences a force upward, this will experience a force downward. So, there are going to be two forces on this coil. On the right side, the force will be upward. On the left side, the force will be downward. What will those two forces do? Those two forces will rotate the coil. And so, we're now going to look at the torque. You understand the word. We have done that in Physics 1. These two forces will actually produce a torque. Now, imagine you have a ruler here. There is a force upward on one end, a force downward on the other end. These two forces will rotate it. Okay, so once